Welcome to another deep dive. This time we're going super small, like unbelievably tiny.
Smaller than small?
Exactly. We're talking atoms.
That's right, atoms.
The listener sent in some IGCSE chemistry notes.
Oh, I love these.
Yeah, so we're going to take a deep dive into those today.
Awesome.
You know, sometimes you just got to go back to the fundamentals of chemistry to really appreciate the complexity of everything.
I agree.
So they start out by talking about, elements and compounds and mixtures.
Chemistry 101.
Yeah, you got it. So how would you describe an element?
Well, an element, think about it as like a pure ingredient.
Okay.
Like when you're baking, you have flour, sugar, eggs.
Yeah,
Those are your elements in the universe,
got it.
right? And there's only a certain number of them, only 118.
Wow, that's it.
That's all we got. And they each have their own kind of unique personality and characteristics.
Like Lego bricks.
Exactly like Lego bricks.
So then compounds, what are those?
So compounds are when you take those elements and you mix them together chemically in a reaction, and you get something totally new.
Oh,
So it's like taking your flour, sugar, and eggs and baking a cake,
okay.
right? Suddenly you have this delicious cake,
Yeah,
which has completely different properties than the individual ingredients.
I see. So it's not just like flour, sugar, and eggs mixed together.
Right, exactly. It's a whole new thing
Got it.
with new properties.
That makes sense.
Yeah.
So what's a good example of a compound?
Water.
Good
As an example, water is a compound
Oh, really?
made from two gases, hydrogen and oxygen.
Wow.
And when they combine chemically,
Yeah.
they form water, which has properties nothing like hydrogen or oxygen on their own.
That's amazing.
Right? So the listener actually provided this cool particle diagram.
I love you.
It shows like the individual atoms of elements, just floating around.
Mm-hmm.
And then it shows like molecules of a compound where the atoms are actually joined together.
Oh, I see.
And then finally it shows a mixture,
Okay.
which is just like different molecules all hanging out together, not chemically bonded.
Yeah, that makes it really easy to visualize.
It's a great way to see it.
So I guess that brings us to mixtures.
Right, so mixtures are more like, you're just throwing a bunch of ingredients in a bowl.
Okay.
They're all coexisting peacefully,
Mm-hmm.
but they're not chemically bonded.
Got it.
So you can easily separate them, like a salad.
Okay.
You can pick out the tomatoes from the lettuce.
Right. Yeah, that makes sense.
It's a physical separation, not a chemical one.
So we've got a limited number of these elements, right? These Lego bricks.
Right, 118.
But an unlimited number of compounds that they can create.
Right, because you can combine them in so many different ways.
Wow, that's incredible.
And in so many different ratios, too.
That's mind-blowing.
Yeah, it is.
So to really understand how these compounds form, we need to zoom in.
Way in.
Yeah, to the structure of an atom itself.
The heart of matter.
Yeah. Have you ever wondered, what makes one element different from another?
Oh, yeah, all the time.
Me too.
Mm.
The answer lies in the atom.
It's all about the structure.
So what is the structure of an atom like?
Well, we often use the analogy of like a miniature solar system
Oh, okay.
with a dense nucleus in the center and then electrons orbiting around it.
Like planets around the sun.
Exactly.
So the nucleus is like the sun.
Yeah, you can say that.
But this solar system, it's mostly empty space, right?
Mostly empty space. It's mind-blowing.
I know the source even says that if the nucleus were the size of a marble,
Okay.
on a football field, the electrons would be like tiny specks
Wow.
whizzing around in the stands.
That's hard to imagine.
It really is.
So much empty space.
I know, and almost all of an atom's mass
Almost all of it.
is concentrated in that tiny nucleus.
It's incredible.
It really is. Okay, so speaking of mass,
Yeah.
the source mentioned something called relative atomic mass.
Right. Have you heard of this?
I have, but refresh my memory.
Sure. So basically, it's how we compare the masses of different atoms,
Okay.
because weighing them on a traditional scale is impossible.
They're way too small.
Way too small.
Right, and they use carbon-12 as the reference point.
Yeah, carbon-12.
So why carbon-12? Why is that the standard?
Well, they needed a reference point, right?
Right.
And carbon-12 happens to have 6 protons and 6 neutrons,
Okay.
making its atomic mass a nice even 12.
Ah,
So it was a practical choice,
got it.
and it's stuck ever since.
Like choosing a standard measurement for length.
Exactly.
Everybody agrees to use a meter stick.
Right.
So we can all be on the same page.
Makes sense.
Okay, so let's meet the subatomic particles
Yeah.
that call this tiny atom home. We've got protons, neutrons,
And electrons.
and electrons, right?
The three amigos.
So where do they all hang out?
So protons and neutrons, they like to hang out together in the nucleus.
Okay.
Like two peas in a pod, they have about the same mass.
Okay.
But protons have a positive charge,
Uh-huh.
and neutrons are neutral, hence the name.
That makes sense.
And then we have those tiny little electrons zipping around outside the nucleus.
Those are the ones with the negative charge, right?
Yeah, they're negatively charged.
It's like a perfectly choreographed dance.
It is a dance.
With those opposite charges.
Yeah.
Keeping everything balanced.
In perfect harmony.
So to understand how atoms interact with each other, we need to talk about atomic identification.
Atomic ID cards.
Ooh, so each atom has its own unique fingerprint.
Exactly. Each one is unique.
Cool. Okay, so tell me more about that.
So we have the atomic number,
okay,
represented by the letter Z. And that tells us the number of protons in an atom.
Oh.
So that's what defines the element.
Okay.
So, for example, every carbon atom, no matter where you find it, has 6 protons.
Okay.
Making its atomic number 6.
Got it.
So if you know the atomic number, you know what element you're dealing with.
So if it has 6 protons, does that mean it also has 6 electrons?
You got it in a neutral atom.
Yeah.
The number of protons and electrons are always equal.
To balance things out.
To keep things balanced, exactly.
Okay, cool.
Yeah.
So then what's the mass number?
Okay, so the mass number, represented by the letter A, is simply the total number of protons and neutrons.
Oh, okay.
In the nucleus. So it gives you a sense of the atom's overall mass.
So let's take an example from the notes.
Okay, love examples.
Copper has an atomic number of 29.
Right, copper.
And a mass number of 63.
63, got it.
So walk me through how we figure out how many protons, neutrons, and electrons it has.
Okay, so the atomic number tells us there are 29 protons.
Okay, 29 protons.
Right. And since it's a neutral atom, we know there must also be 29 electrons.
Okay, got it.
Now, to find the number of neutrons, we simply subtract the atomic number from the mass number.
Okay.
So 63 minus 29
equals
34 neutrons.
Oh, that's like a little puzzle.
It is. It's a fun little atomic puzzle.
I like it.
Yeah.
So once we understand this, it really opens up a whole new world of understanding about how elements behave and interact.
Absolutely. It's the foundation of chemistry.
Speaking of unique identities, we need to talk about isotopes.
Ah, isotopes, those tricky little things.
Right. So remember those siblings we mentioned?
Yeah, the atomic sibling?
Well, isotopes are atoms of the same element.
Same element.
With the same number of protons, but a different number of neutrons.
So they're like fraternal twins. They share some characteristics, but they have their own distinct personalities.
That's a great way to put it.
Right.
But if they have the same number of protons, wouldn't they behave the same way chemically?
That's a great question. And the answer is yes. Isotopes of the same element have nearly identical chemical properties.
Oh.
But those extra neutrons can cause subtle differences in their physical properties.
Like what kind of differences?
Well, think about density, boiling point, even radioactivity.
Okay.
Take hydrogen, for example. The most common isotope, hydrogen-1, has 1 proton and no neutrons.
Okay.
But there's also deuterium, or hydrogen-2, with 1 proton and 1 neutron.
Oh, so it's still hydrogen.
Still hydrogen.
But it's just slightly heavier.
Slightly heavier because of that extra neutron.
Because of that extra neutron, and the notes mention a third isotope, tritium.
Tritium, right.
With 1 proton and 2 neutrons.
That's a heavy one.
It's fascinating how these tiny variations
can
have such an impact.
Huge impact.
But we've been so focused on the nucleus.
Yeah, we have.
We haven't even talked about those energetic electrons.
Those speedy little things.
Whizzing around it.
We'll get to those.
Yeah, in the next part of our deep dive.
It's time to explore the world of electron shells.
I can't wait.
Me either.
Okay, so we've explored the nucleus, but now it's time to zoom out and talk about those electrons.
Right, those busy little things.
Yeah, the notes mention electron shells.
Oh yeah, electron shells.
Which sounds kind of like those Russian nesting dolls.
That's a great analogy.
So are the electrons just randomly bouncing around in these shells?
Not at all. They're actually very organized. You know, like passengers on a crowded train. Everyone wants to be in the most comfortable spot.
Okay, the best seat.
Yeah, and in an atom, that means electrons want to be in the lowest energy levels first.
So close to the nucleus.
Exactly, because that's where they're most stable.
So it's all about finding the best seat close to the action.
I like that analogy.
But how many electrons can fit in each shell?
Ah, well, that's where those filling rules come in.
Okay, filling rules.
Yeah, so the first shell, the one closest to the nucleus, is like a cozy 2-seater. It can only hold 2 electrons.
Okay, so first come, first serve for those prime seats.
Exactly, those are the best seats in the house.
What about the next shell?
Okay, so the second shell is a bit bigger.
Yeah.
Like a train car that can hold up to 8 passengers.
8.
And for the first 20 elements we're talking about, the third shell also holds 8.
Oh, okay.
Although it can technically hold more.
Got it.
But we're keeping things simple for now.
So we start filling those shells from the bottom up, like carefully placing passengers on the train.
Exactly. Making sure everyone has a seat.
The notes provide a helpful table showing the electronic configurations for the first 20 elements.
Oh, those are handy.
It's really interesting to see how those numbers relate to the number of electrons in each shell.
Yeah, it all starts to make sense when you see it laid out like that.
And here's where it gets even cooler.
Okay, I'm intrigued.
This electron arrangement, this configuration,
yes,
it's reflected in the organization of the periodic table.
Oh, I love the periodic table.
Wait, so the periodic table isn't just a random chart on the wall?
Not at all. It's a brilliant system that reveals the underlying structure of atoms.
Wow, so it's like a map?
It is a map of the elements.
So tell me about the organization.
Okay, so the elements are organized into vertical columns called groups.
Groups.
And elements in the same group share similar chemical properties.
Oh, why is that?
Because they have the same number of electrons in their outermost shell.
Oh.
Which we call the valence electrons.
So those are the electrons that interact with the outside world.
Exactly. They're the social butterflies of the atom, the ones making connections.
That makes sense. What about those horizontal rows?
Those are called periods.
Periods.
And they correspond to the number of occupied electron shells.
Okay.
So elements in the second period have 2 occupied shells, while elements in the third period have 3, and so on.
It's all beautifully organized.
It's a masterpiece of organization.
I never realized how much information is packed into the periodic table.
There's a whole universe in there.
So the source highlights the noble gases.
The noble gases.
Those elements in Group 8.
Yes. The special ones.
They're known for being unreactive, but why is that?
Well, they've achieved a state of Zen-like stability.
Zen-like?
Because their outermost electron shell is completely full.
Oh, okay.
They're content. They have no desire to gain or lose electrons.
So they rarely react.
Exactly. They're like the hermits of the periodic table.
They've won the game of atomic Tetris.
They've got all the blocks in place.
And all the other elements are striving to achieve that same stability.
That's the driving force behind chemical bonding.
So they want to gain, lose, or share electrons.
Exactly. They want to fill that outermost shell and achieve that noble gas configuration.
It all comes back to those electrons and their desire for stability.
It's a never-ending quest for stability.
So how does the concept of isotopes fit into all of this?
Right. So remember, isotopes are atoms of the same element with different numbers of neutrons.
Yeah.
And while those extra neutrons don't affect the atom's chemical behavior, they can influence its physical properties.
So if isotopes are chemically identical, how can they have different physical properties?
It all comes down to mass. Those extra neutrons add a bit of weight to the atom.
Oh, I see.
Which can affect things like density, boiling point, even radioactivity.
It's amazing how these tiny variations at the atomic level can have such a big impact on the properties of matter.
Yeah, it really highlights the interconnectedness of everything.
Can you give me an example of how isotopes are used in the real world?
Absolutely. So, for instance, carbon-14.
Okay, carbon-14.
Which is a radioactive isotope of carbon. It's used in archaeology to date ancient artifacts.
Oh, wow.
And in medicine, radioactive isotopes are used for imaging and even cancer treatment.
Wow, that's incredible.
It really shows the power of these tiny atoms.
It's mind-blowing to think that these tiny variations at the atomic level can have such a significant impact on the properties of matter.
It's the beauty of the atomic world.
This deep dive has given me a whole new appreciation for the complexity hidden within seemingly simple things.
I know, it's amazing, isn't it?
Who knew atoms could be so fascinating?
There's so much more to learn.
So what does all of this mean for our listener? Why should they care about atoms and isotopes?
Well, understanding the fundamentals of atomic structure is like unlocking a secret code.
Oh.
It allows you to decipher the language of chemistry and appreciate the incredible complexity of the world around you.
Yeah.
From the food you eat to the air you breathe, everything is made up of these tiny building blocks.
We've seen how those tiny building blocks, those atoms, strive for stability, leading to the formation of chemical bonds and the creation of an astonishing diversity of molecules.
And that's just the beginning.
But here's a final thought-provoking question to leave you with. How do these atoms interact to create the materials and substances we encounter every day?
What forces hold those atoms together?
Something to ponder. It's like a whole new world opened up to me.
It is.
Those atoms, those tiny little things.
Yeah, they're amazing.
So they're interacting to create everything.
That's right.
What forces are actually holding those atoms together?
Well, think of it like this. Atoms are like tiny Lego bricks, right? And chemical bonds are the connectors.
Okay. I like that analogy.
Right, so just like Legos, you can build all sorts of different structures by connecting them in different ways.
Right, so atoms can combine to form all the different materials we see around us.
Exactly. And just like Legos have different kinds of connectors, atoms have different ways of bonding with each other. Some bonds are strong and rigid, some are weak and flexible.
I see.
It all depends on how the electrons are shared or exchanged between those atoms.
So the type of bond determines the properties of the material.
Exactly.
Whether it's a solid, liquid, or gas.
Right.
Or how strong or brittle it is.
You got it.
Okay, that makes sense. So let's take water, for example.
Okay, water.
It's a simple molecule, right?
Simple, but powerful.
Yeah, 2 hydrogen atoms bonded to 1 oxygen atom.
Right.
But those bonds are incredibly strong.
Oh, yeah, super strong.
Which gives water its unique properties.
That's right. It's a liquid at room temperature. It has a high boiling point. It can dissolve all sorts of things.
It's amazing how those tiny little bonds have such a big impact.
It's all about the electrons.
What about something like a metal?
Okay, metal.
How are those atoms held together?
So metals have a special type of bond called a metallic bond.
Metallic bond?
Yeah, in a metal, all the valence electrons, those outermost electrons, they're kind of just loosely shared among all the atoms.
Okay.
Creating what we call a sea of electrons.
A sea of electrons?
Yeah, it's like they're all swimming around together.
So that's why metals conduct electricity and heat so well.
Exactly. Those electrons are free to move around, carrying energy with them.
I see. So we've covered a lot of ground in this deep dive.
Yeah, we have.
We started with the basics of atoms.
The building blocks.
Then we explored their structure.
Right.
And zoomed out to see how they interact to form the world around us.
It's a pretty amazing journey when you think about it.
It really is, from the infinitely small to the incredibly vast.
And we're still learning so much.
Yeah, there's always more to discover.
Absolutely. Science is a never-ending quest for knowledge.
So to our listener, we encourage you to keep exploring, keep asking questions, and never stop being curious.
That's the key to understanding the universe.
The world is full of amazing discoveries just waiting to be made.
So keep those neurons firing.
And we'll see you on our next deep dive.